Oh, yeah. Okay, our speaker today is Bobby Gramacy. He is a professor and also the department head of the Department of Statistics at Virginia Tech. He got his PhD at UC Santa Cruz and then spent a number of years as a faculty member at Cambridge and at Chicago Booth, and then moved to Virginia Tech about 10 years ago. Bobby is extremely productive. In addition to writing a lot of papers and software, he's also, as I said, the department head at the moment, and he served as editor of the journal Technometrics for a couple of years, and also wrote 2 books in recent years. He's won a number of awards, including the Savage Award from ISBA, and was elected fellow of the ASA a few years ago. His research interests include surrogate modeling, UQ, Gaussian processes, Monte Carlo inference, and today he'll actually tell us about Gaussian processes, specifically monotonic warping for additive and deep Gaussian processes. Please help me welcome Bobby.
Thanks, Matthias. Thanks to everyone. It's a pleasure to be here and to speak with you. So I'm going to talk to you today about Gaussian processes. I'm going to give you a little bit of a review to start with.
It doesn't show up here.
It doesn't. Well, I can go. What do you want me to do?
Okay, there we go.
Okay, I can click OK.
Yes.
Okay, I'll tell you about Gaussian processes. Review them for you 2 different ways. So this slide is the first way, and then I'm going to give you another review a few moments later. So Gaussian processes are popular as a non-parametric regression machine in many areas. Geostats, surrogate modeling, which is my area, computer simulation experiments, and in machine learning. And the reason they're popular is that they're flexible, nonlinear, give smooth input-output relationships. They're accurate and have good uncertainty quantification. But maybe the most important thing is this bullet in the middle. They have a high degree of analytic tractability, by which I mean you boil the inference down to linear algebra. So the plot here I have is an interpolation of 8 observations of sine of x, and the R code generates that figure. You can see it's about 15 or 16 lines of R code, but the most important parts of that R code are really just these 2 equations doing some matrix vector multiplication. So that's what I mean, that there's a high degree of analytic tractability. I'm going to show you where these equations come from over the next few slides. Okay, so how does that work? We're going to model random functions under a multivariate normal distribution. If I have some inputs x, and I build an n by n covariance matrix with those n inputs, that is a function of inverse distance. So the ij entry in that matrix is e to the minus xi minus xj squared. I build that n by n matrix and plug it into my favorite random multivariate normal number generator, in this case with a 0 mean, and then plot for you those xy pairs. I'll have a nice smooth function. It won't exactly look like sine of x. That's where the learning part comes from. So I can build a covariance matrix like this for training data using the x's that are my inputs for the training data, and I can also do it for testing data where I don't know what the y's are, and then I can consider their joint multivariate normal and use standard multivariate normal conditioning rules to work out the distribution of the testing locations given the training locations. So the way that that works is, used to be you would find these identities in the appendix of a good textbook, but now you can find them on Wikipedia. So this is stolen directly from the Wikipedia page for multivariate normals. If you partition a random vector y into 2 parts, y1 and y2, with means mu1 and mu2, and then a 2 by 2 block covariance matrix for y1 and y2, and then condition y1 on y2, it's just linear algebra. You can work out the mean of that multivariate normal as a projection, and then the covariance as a kind of difference between the marginal and the conditional covariance. If I apply that with the setting that I just showed you involving inverse distance-based covariance functions, then you get these equations. You get that the prediction at a new set of inputs, a testing set of inputs, squiggly x, given some training data x and y, is a linear projection of those y's in some kind of inverse distance space, and then a quadratic reduction of variance from the marginal variance. So it's just linear algebra. These are those two equations that I showed you earlier in our code that give that interpolation of training observations that came from sine of x. These are called the Kriging equations, which is a word that's used a lot in mining and geostatistics. They have all sorts of great properties, and this talk isn't about those properties, but one of them is that they describe the best linear unbiased predictor. Okay, so that's my first review of Gaussian processes. Here's my roadmap for the rest of the talk. Maybe that went too fast. I'm going to do it over again, I think, in a simpler way, in a way that I've recently found attractive for understanding what's going on, and I'm going to use a slightly different tool. Instead of using linear algebra, I'm going to use elliptical slice sampling. And along the way, we'll introduce what I call a reference process that's important for some of the contributions that I'll tell you about in the second half of the talk. And those contributions are monotonic Gaussian processes, and then an application of those monotonic Gaussian processes to deep Gaussian processes. Deep GPs has been an area of interest of mine, and I'll tell you more about that sort of in the latter third section of the talk. Okay, so that's the plan. So a second review. This isn't really a review. This is kind of a new way to think about it. It's not. I'm not new in the novel sense. I don't think I made it up, but hopefully this will help you, and it'll help frame some of the other things that we're going to talk about in the rest of the talk. So suppose I want to model data. I'm thinking about it in a regression context. I have pairs of x and y. X can be in any input space, and y for this talk is going to be scalar, but I think you can generalize it to other situations. And I'm going to model the y's as a function of, as an unknown function of the x's. The unknown function I'm calling f, and I've got some parameters mu and nu that center and scale the function. And then I've got some IID errors, epsilon. The center and scale are not super important for this part of the talk. I'll use them a little bit later. So if it helps you think about it, you can put 0 for the center and 1 for the scale. And really the emphasis is on the unknown function f. Okay. All right, we're going to suppose that f follows an inverse distance-based multivariate normal, sort of just like I showed you a moment ago. So my f's, not the y's directly, but the f's have this multivariate normal prior, still zero mean, covariance function that is distance-based. I've embellished this distance-based function to have length scale parameters. So this is a parameter that governs the rate of decay of correlation as a function of distance separately in each input direction, in each Euclidean input direction. So those are called length scale hyperparameters. The function defining C is sometimes called a kernel. There are many kernels that are fine. This is a very simple one. This talk isn't about the kernels. Distance is an important feature in many Gaussian process regressions, but even distance is not absolutely essential. Okay, so for now, fix these scalar hyperparameters so the focus is on the random function outputs f. So I've got that these f's are multivariate normal. That's going to be my prior. And the likelihood is the IID noise, basically, the Gaussian noise that I put on the observations y, given the unknown function values f. So that's my model. It's a Bayesian hierarchical model for outputs y given inputs x. It's a regression model that uses Gaussians in two different ways. How would you perform inference for the unknown quantity? The main unknown quantity is the f's. Those parameters are also unknown quantities, but let me table those for right now. So Bayes' rule says that the posterior distribution over those unknown function values f is a product of likelihood and prior divided by marginal likelihood, or divided by that integral. And it's that integral that usually makes Bayesian inference difficult. But actually, in the context of Gaussians, you can do that integral in closed form if you're a good integrator. So there's a high degree of analytic tractability. You can do the prediction equations through multivariate normal identities, and you can convolve these two normals together in pen and paper and work out what this normalizing constant is. And you could use this, sometimes called the marginal likelihood, to perform inference for other unknown quantities like the hyperparameters that I showed you on the other slide. But I'm not going to show you what the outcome of that integral is. Suppose you're not good with integrals or not good with the linear algebra behind the multivariate normal conditionals that I showed you earlier. What could you do instead? One thing you could do is Monte Carlo or Markov chain Monte Carlo. Depending on how you set that up, that is probably not going to be easy. This F quantity, I've got one unknown function output for every input. So I've got n of them. That's a high dimensional unknown or latent variable. So it's going to be difficult to do like Metropolis style sampling for all of those coordinates. It's going to be hard to optimize a joint proposal that has a good rejection rate. So you're probably going to get a sticky chain. And you could go coordinate-wise. That would increase your acceptance rate, but would mix really poorly. You'd move it very inefficiently throughout the space of this latent variable. A cool algorithm, though, that is kind of recent, I don't know if you think about 2010 as recent, that I discovered, or rediscovered actually a few years back, is elliptical slice sampling. And ESS is ideal for this situation. It's applicable whenever you have a Gaussian prior for the unknown quantity. It can be a multivariate Gaussian, and any likelihood. But in this case, we also have a Gaussian likelihood. ESS also gets used in this context for other likelihoods, like Bernoulli likelihoods under a logistic transformation. You could use that for classification, or Poisson likelihoods under a log transformation, which you could use for Poisson regression, and so on. But here we're just sticking to Gaussian likelihoods in a standard real valued regression setting. How does ESS look? I don't know if it's really reasonable to ask you to follow this diagram. So I'm not going to take you through it line by line. I'm just going to point to some important parts of it. You need to be able to generate from the multivariate normal, which you can do with a multivariate normal random number generator. And you need to be able to do a linear combination. You're actually walking around an ellipse in this algorithm, which is why it's called elliptical slice sampling. So that in that step, you're combining a draw from the prior with the previous draw that you have. So you're creating a Markov chain, and you're kind of walking in this space around an ellipse that involves prior draws. And you accept this proposed elliptical combination by looking at a likelihood ratio. So it's a little bit like Metropolis, but the difference is that if your proposal is rejected, you just adjust where you are on the ellipse. And you keep doing that until you accept. So it really is a rejection-free sampler in the Metropolis sense. It's not going to create a sticky chain. You do some rejections, but then you make an automatic adjustment until you can accept one of these proposals. So you're really only making one multivariate normal proposal. The rest of it is all simple arithmetic on an n vector until you accept. So here's an illustration. Suppose I started my Markov chain with the solid black line. So that's just this horizontal line here that's in the figure. And my training data is the open circles that you see on the plot. What you would do is you'd propose a random vector, and then you'd take this linear combination with the previous one. So I don't know if you can see colors or not really, but there's a solid red line, and then there's a few dashed lines. So each one of these dashed lines is one of the proposed next values. 3 of them were rejected before the solid one was accepted. So it took 4 iterations through this loop to find one that was accepted. And then it was accepted, and now it becomes the next vector of function outputs. And then we make another proposal from a multivariate normal, and we do that elliptical combination, and then I think that color is green. So we have one, maybe only one expected green one before we get the accepted. And that's how the algorithm goes until I think the last one here is that magenta. I suck at colors. It's a reddish purple one. Okay, so that's the algorithm in action. This is a one-dimensional example, but the input dimension is not a factor, at least not for the technical details of the algorithm. For its implementation, it could make things more complicated. So everything except sampling from the prior is at worst order n. Generating from the prior, if it's a dense covariance matrix, which it would be given the one I gave, you'd have to do a cubic calculation, usually by Cholesky. The mixing of this Markov chain is excellent. It's typical to have only 3 or 4 rejections before you accept one, and it moves throughout this high dimensional space very efficiently. If you want to do prediction, then you make your proposed function outputs for the testing locations at the same time as the training ones, but you base the acceptance only on the training ones, and you keep whichever testing ones went with it when it comes for prediction. That's your testing prediction. Actually, the lines that I showed you in the previous slide were actually predicting lines. They were on a grid of 50 inputs, so I could make a nice smooth curve, right? With just these 20 points, I wouldn't have nice smooth curves. Curves come because I used a grid in the input space, and I did the sampling on that grid along with the ones that went with the training data, so I could make a nice plot. Okay. So anyone who knows anything about Gaussian processes knows that this cubic calculation, where I've got to generate from the prior in this case, or it's involved in any of the other things that I showed you earlier, which are different, really limits the training and testing data sizes that you can use with Gaussian processes when dense matrices are involved. So in this graphic, this is a graphic that corresponds to some later things in the talk that I haven't told you about yet. But the important thing is the GP line here. The time is like very quickly increasing after you get to, a few dozen input locations. And in practice, it's computationally feasible to work with these cubic matrix decompositions with a few thousand training data or testing locations. But beyond that, it becomes pretty cumbersome. Some of the other methods that I'm going to tell you about are nicer. They have these flatter lines. There are so many good ways to work with sparse or low rank matrices in order to speed up Gaussian process calculations. The Vecchi approximation, which is Matthias's huge contribution, I think, in the last 10 years. I don't know if he would say it's his most important one, but it's been the most important one to me. It's a really great way to work around these big matrix calculations. But I'm going to tell you about a slightly different one that's ideally suited to some of the other stuff I want to tell you about later in the talk. Okay. So I'm going to define something that I'm going to call a reference process. And I'm going to stick to one input dimension, although I don't think this is a big deal for a few reasons, in part because what I'm going to show you later is really just a combination of many one-dimensional reference processes, although I think you could do this in higher dimension. All right. Rather than work directly with the unknown function outputs at the training data locations, I'm going to instead use an auxiliary grid, xg, and work with the outputs at those locations instead. My grid is just think equally spaced inputs in the input space. That's xg, and fg is the unknown function locations at those grid points. It's a little bit like making a prediction, although I want to create a new set of variables so I can separately talk about training data, predictive locations, and then this third new thing, which is the reference process. The idea of setting up this process is similar to the way Sudipto talks about knots in Gaussian process regression, or as part of what's known as a predictive process, or inducing points, which is a really popular way in the machine learning community to create a low rank covariance structure. But it's neither of those two things. My grids in this talk will almost exclusively have 50 points in them between 0 and 1. Okay. So in my elliptical slice sampling algorithm, I'm not going to propose function outputs for the training data. I'm going to propose them on this reference grid. And then I'm going to use linear interpolation to map them to the corresponding outputs at the training data, and also anywhere that I want to make a prediction. Okay. So my prior is still multivariate normal, but not on the training data locations on the grid. I use LIs just for linear interpolation. I linearly interpolate those to the outputs at the training data locations, and I have the usual Gaussian likelihood. That has not been changed from before. So here's a little picture that describes that. So I've got a draw from a multivariate normal at some training data locations. Those are the open circles. This is just a random draw, a random function. And instead of using those values, I've specified a grid. Actually, my grid has 25 locations because I wanted to make it easier to visualize. Those are the red circles or the red dots, and I've used straight lines to interpolate between them. And my point in making this plot is that the red line doesn't look that different than the curve traced out by the actual open circles. It's a pretty good approximation. You can play with the grid density if you want to. This is a little plot showing you low density grid, high density grid. This is 100 points. This is 10. This is 50. To the eye, 50 is wonderful. You can't tell that it's actually linearly interpolated. It looks like a smooth curve. In fact, the way that R draws smooth curves is by connecting little line segments. Your eye just can't see those little line segments. So I think this is, at least in one input dimension, this is a really great way to cap the computational effort, because I'm only ever working with a 50 by 50 matrix, which I can decompose very quickly. And I get curves that look like they're much higher resolution. The computational cost is attractive, and yeah. Very good. Wonderful point. I don't have a good response. I think you're right, but I don't know. Okay, so that ends my kind of review, and there's a little bit of a new idea in there, which is the reference grid, which I'm going to use in the second part of my talk. Okay, so I'm going to tell you about monotonic Gaussian processes. What am I thinking is a monotonic Gaussian process? This is one where the function that I want to learn is monotonic. So in one input dimension, that means as my x's track from left to right, the function is increasing or not decreasing. Okay, or it could be the other way around. It could be decreasing, not increasing. Okay, so why bother with setting up this new way to think about Gaussian processes through elliptical slice sampling and the creation of this reference grid? Because those two things let me muck around with my prior over the function space in a very simple way. So how would I adapt this algorithm to generate functions that were increasing or not decreasing? I could do it in the following way. I could first suppose that my inputs are ordered, which is, they're one-dimensional inputs, so that's easy. Just sort them. And then generate the z's from a Gaussian with a distance-based covariance matrix. And then exponentiate them to make them positive. Take their cumulative sum so that they're increasing, and then renormalize. That's what these three steps say. And then these Z3s, which I'm going to call F, will be increasing as you go from left to right. And so here's here's how that looks. Every gray line is a draw from a typical Gaussian process prior. It's a wiggly function, but then I exponentiate it and do the cumulative sum and renormalize, and I get that they're all increasing now. Each one of them is a random function, but they have this property by construction that makes them increasing. And I'm sure you can think of other constructions that would have the same flavor. And we've tried a few other ones, and I'm not going to talk about it. Just let's stick with this one. And maybe you have some others in mind that have other properties besides monotonicity. We've been playing with those too, but I'm not going to talk about them. Okay? So here's how this would work in our elliptical slice sampler. It's the same algorithm. I'm still going to be drawing from the prior, and I'm still going to be working on this ellipse. But right before I use it in my acceptance step, I'm going to, it says enforce, but a better word would be construct monotonicity. I'm going to take this Gaussian draw and exponentiate it and do the cumulative sum and renormalize so it's increasing. And then I will try to accept or reject that instead. On this slide, I'm admitting that there's a possible snag to this, which is that the cumulative sum means that everything is related to whatever points you've given it at that moment. If you're working with training data only, the cumulative sum would be on that training data. If you're doing it with testing locations, you better do it at the same time as your training data. Otherwise, you're going to have a discontinuous function. So here I'm showing you what it looks like at the same, what it looks like for some testing locations and training locations beforehand. And this is what it looks like after. If you do them jointly, it's nice and smooth, but if you do them separately, it messes it up. So you have to handle your training and testing data at the same time. You have to specify in advance where you want to predict, or you can't use this algorithm, except if you use a reference process. If you anchor everything to these locations that I called XG, and then derive from XG what it would look like for the training data and for the testing data, then you don't have to specify your testing locations in advance. And this is really the origin of the reference process, at least in terms of our own research. We created it for this, but I decided to tell you about it in a different context. So I'm going to be, when I write mono of z, I just mean that you're going to exponentiate and then cumulative sum and then renormalize. That's my monotonic transformation. I'm going to do that on the reference grid, and then I'm going to linearly interpolate to the training data or to the predictive locations, depending on the context in which I want to use it. So the full hierarchical model, I don't know, if you're a Bayesian, you love these things. If you're not, you hate them. So it's okay if you gloss over. I just want to write everything out that's random using likelihoods and priors for the whole model. The likelihood is Gaussian. The linear interpolation happens at the training data locations after monotonic transformation. I've got priors. It's still a Gaussian process prior, but it's on the reference grid, not on the training data itself. And then I've got standard priors for some of the other scalar unknowns, which until this point I had glossed over. I had just fixed values, but now I'm going to include them as unknowns with standard priors. So everything is pretty ordinary as Gaussian process modeling goes, except this reference grid and monotonic transformation. But those things work really nicely within the elliptical slice sampling framework, and the other choices for priors make posterior inference kind of straightforward. I'm going to take you through the next few slides, but if you have experience in Bayesian stats, you'll recognize that what I'm showing you here is not novel. It's just basic metropolis within Gibbs sampling. So the way that I've set up the unknowns mu and nu, I can integrate them out of the model in closed form and get a tidy expression for the marginal likelihood for those two unknown parameters. So they can be done with metropolis sampling. Well, it's actually Gibbs sampling within a metropolis. With prediction, I get a student T family of predictive equations, which are very similar to what you would get if you were doing Bayesian linear regression, except in this case, it's linear in the unknown function values, which are Gaussian processes, so it's nonlinear. And you could save samples from the posterior distribution if you want to, or you can collect moment-based averages, which is usually more efficient from a storage perspective. So all the predictive equations that I'll show you will involve both draws from the posterior so you can see all of them, but also summaries based on averages of the means and averages of the covariances. So these aren't exactly averages, but it's law of total covariance averages of variances. Okay, pictures. So here is some data. The open circles are data that was sampled with noise from a logistic curve. Just a very simple one-dimensional toy example that I want to do regression on under a Gaussian process, but I want to leverage that I know that the function is increasing instead of just some function that could be anything. One of the fits in this plot, the one that says GP, is the one that doesn't use the monotonicity assumption. You can see that it has curvature here. It turns back around. Same thing on the other side. It turns back around because it doesn't know that the function is a logistic, that it's increasing. But my mono GP does know that because it's built into the prior, and you can see that it never turns around. And none of the gray lines, which are samples from the posterior, turned around. It's not just on average monotonic. Every sample from the posterior distribution is monotonic. Its summaries are monotonic. I've got monotonic error bars formed as credible intervals point-wise. I've got really good mixing for the unknown hyperparameters. I know what the truth is, and I'm getting good mixing around the truth. Very simple problem. How do you handle multiple inputs? Well, you just do the same thing additively. This is not the only thing that you could do, but it's the simplest thing that you could do. I specify that I have an additive function of monotone functions in each input direction. It's very difficult to define monotonicity in high dimension, but this is one way that you can do it. There are other ways, but I think this is by far the simplest way. So I've got an additive function where in p dimensions, I have p sets of latent variables f. Each one of those is assumed to be monotonic under my prior. And then I just need to learn what the center and scales of those monotone functions are, which I can put into my Gibbs sampler or my metropolis within Gibbs with a for loop. So coding-wise, it's a simple extension. Here's an example toy problem. The truth is shown to you in the top right in terms of inverse logistic functions. And some of the other hyperparameters that were used to generate the data are shown on the top right. On the left, I have what I would predict under a monotone Gaussian process. And here's on the right is what I would predict under an ordinary Gaussian process. I think the one here looks better. I'll show you some empirical results in a minute. This one doesn't look like it's as confidently seeing the two logistic functions. Maybe the most important thing is the way that this prior treats uncertainty. On the left is my uncertainty using a monotone one. There I'm getting uncertainty where the function slope is high. Right? This is where it's changing direction the fastest. Here I'm just getting uncertainty at the edges of the input space, which is where I have less data. Here is a view along the diagonal. It's a two-dimensional function, right? And I'm just looking at that function along the diagonal in two input directions to show you that the ordinary Gaussian process is not monotonic. Again, it's got curvature here. It shouldn't have, but the monotone one doesn't have that problem. I can also look at the latent variables compared to the truth because the way this data was generated, I know what the true functions are in each of the additive components. And my samples from those functions are very close to the true functions that generated the data. In an out-of-sample benchmarking exercise, I get more accurate predictions compared to an ordinary Gaussian process and a better UQ in terms of cumulatively ranked probability score compared to an ordinary Gaussian process. This middle thing, LinEQ-GP, is a competitor method that targets constrained Gaussian processes like monotone Gaussian processes. Involves some similar ideas, but doesn't use elliptical slice sampling, doesn't use the reference grid, and doesn't use the transformation that we do, but otherwise has some features in common, but isn't as good in this case. So that was, I showed you a one-dimensional example and a two-dimensional example. Here's a five-dimensional example that comes from the paper of our competitor method. And I can show you what our inference for each of the individual functions is, and it's pretty good. I can show you what our predictions are along the diagonal in this five-dimensional space to show you that an ordinary Gaussian process is not monotonic. And so that's the reason it doesn't predict as well. Our method and the competitor method are very similar in this example, but both of us beat an ordinary Gaussian process because the ordinary Gaussian process is trying to work in this five-dimensional space and it doesn't know that the function is monotonic in those five coordinates. Here's a 10-dimensional version where I'm short-circuiting things a little bit that also came from that paper. And you can see that the standard Gaussian process is egregiously wrong. In higher and higher dimension, the information that the function is monotonic is more and more valuable. It helps to constrain your inference to functions that are monotonic. Okay, so that's a monotonic Gaussian process. That takes us through the first two-thirds of the talk. And in the final two-thirds, I'm going to introduce something new and show you about how this idea of a monotonic Gaussian process is helpful. So the something new is a deep Gaussian process. So throw away monotonic in your mind for a second. This is a difficult part of the talk. I'm not talking about anything monotonic. I'm just talking about a Gaussian process. And I want to show you about something called a deep Gaussian process. And I love this graphic. This was made by my PhD student. She's not a PhD student anymore. She's my colleague, Annie Booth. Okay, so here we go. A typical Gaussian process maps x to y's. So a random function draw, in this case, that function draw happens to be monotonic. So don't let that fool you. It's just a curve, right? So that's a set of y's given a Gaussian draw with a covariant structure that's built on inverse distances. Now, suppose I take those y outputs, those y1s, and I stick them in as inputs to another Gaussian process, giving me y2s. So here the y1s are inputs now, and the y2s are the new outputs. And then I plot for you what those y2s look like as a function of the original inputs x. I've created kind of a daisy chain in the same way that neural networks create a daisy chain if they're broad, if they're deep. So I've created a two-layer deep Gaussian process. So these y's went through some Gaussian y1s, which came from some Gaussian relationship in x. And I can keep doing this daisy chain as much as I want. I can put those y2s in to create some y3s. And each time I do that, I'm potentially getting a more wiggly function. And in fact, if you look at the way the original inputs kind of map to outputs, the first transformation is spreading out the inputs because these y's have a steeper slope. Right? The steeper slope is effectively spreading out the original inputs. And then these steeper slopes, the one here and the one here, are spreading out these inputs and those inputs, but they're compressing these. So I'm kind of warping the original input space with these intermediate layers. So this is the way the word warping comes in. These These y1s are warped versions of the x's before they produce y2s, which are then warped in, versions of the y1s before they create y3s. And that warping can be visualized on the original set of inputs. So it's like I'm messing with the inputs by transforming them or warping them before using them to create outputs. In practice, we have found that just having one of these warpings, in other words, a two-layer deep Gaussian process, is sufficient for everything that we do. We work on computer simulation experiments, which are a very particular part of the landscape of non-parametric regression where Gaussian processes are used. I'm not going to make any claims that in machine learning applications you only need two layers, or in geostats you only need two layers. But in our experience, when you're working with computer simulation experiments, two layers are plenty. So I'm going to rewrite this as a hierarchical model. My y's are some warped versions, which is why I'm using W, of the original x's. And if you like these neural networky diagrams, I've got my x's in p dimensions, and they're being warped to p intermediate locations before combining to determine the output y. This warping is a high-dimensional latent variable. If I have p coordinates of x and n training data inputs, I've got an n by p matrix of latent variables that I want to learn as part of my Gaussian process learning exercise. And the way that people have done that historically is with variational inference. You do this integral by replacing it with a maximization, the reference distribution, and some loss. But that's not how we do it. We do it with elliptical slice sampling, using the same exact algorithm that I showed you earlier. You propose W's, and you might move those W's around an ellipse, but eventually you accept or reject them based on the likelihood that they give to the values y that you have in the data. I'm not going to go back over that. If that was too quick, you can check on it in our papers. Here's just a simple example of what that looks like. In this example, I've got a wiggly region in the input-output relationship and a straight region. And my posterior samples of W spread out the inputs that are less than about 0.4 and compress, flatten inputs that are bigger than about 0.4. And that makes sense because I need more space in the input space to learn a wiggly function than I do to learn a straight function. An ordinary non-deep Gaussian process would just have an identity W. It would just be a straight line, but this line has curvature stretching out early inputs and compressing late ones. And it doesn't matter whether you do that in an upward direction or a downward direction, it has the same effect. There's an identifiability problem, but that doesn't impact the pairwise distances that are involved in the likelihood. Here's another example where things don't work quite as well. This example also has wiggly, straight, and wiggly regions. And the deep Gaussian process, which is in green, has a tighter fit. The UQ is better. It's got narrower error bars while still capturing the input-output relationship. But not everywhere. There's some kind of problem going on here. So what is that problem? What's happening is that the training data from two different parts of the input space are being warped in a disadvantageous way. A lot of the posterior sample of warpings is being shown here, and you can see that some of them, in particular this one that I've highlighted for you in black, is not monotonic. It is warping this input here at 0.7 to the same value as this input here near 1. In other words, these two parts of the input space, after warping, are very close to one another. In fact, they're jumping over other training data locations. So the visual of that is, this is what those training data look like before, and this is what they look like after. I've grabbed an output from like a different part of the space, one that's messing with my mapping. If I can make the warping injective, which I can do now that I have a monotone Gaussian process, instead of saying the warping is just a Gaussian process, now I can say the warping is a monotone Gaussian process, and I can fix that problem. I can still compress the middle part of the input space where the function is flat without destroying the relationship between the points at the edge of this space and the points that are part of the wiggly part of the function. Here's a two-dimensional example of this. This is a test case called the cross and tray function. It's a great test case because it has flat regions like at the corners of the quadrants, and it has steep regions at the cross in the middle of the input space. An ordinary Gaussian process, an ordinary deep Gaussian process is able to warp inputs x1 and x2 into w1 and w2 to learn that it's flat here and wiggly there, which an ordinary non-deep Gaussian process cannot do. But a mono warped version of that, where I use a monotone Gaussian process instead, works even better because it can make this cross straight. It doesn't warp it in a funny way where information bleeds from extremes of the input space. And I can also visualize what these warpings look like because they're one-dimensional warpings instead of two-dimensional ones. All right, this is my final slide. If you were hoping I'd have some great example on some difficult applied problem, I do, but not in this context. It'd be a totally different talk involving a PhD thesis of my students, and I didn't want to steal his thunder, and I didn't think I could jam it in. So this is my last slide. We did a bunch of benchmarking. One of them was on this cross and tray function where the monotone version of the deep Gaussian process is the winner. Let me clarify, the deep Gaussian process is not itself monotone. Look, this function goes up and comes back down. It's the warping that's monotone. This is data from my PhD thesis. I developed a method called TGP that uses trees to partition up the input space and Gaussian processes at the leaves of the tree. It was created for exactly this data. This is data on the lift force of a rocket booster as it's re-entering the atmosphere as a function of its speed and angle of attack and the way that it's rotated. So it does really well on this example, and deep Gaussian processes do not do so well unless you use a monotone warping, and then it's just as good as using a tree. This is a much simpler model than the tree version. This last one here is a data set that I've been working on recently. It's an 8-dimensional problem involving predicting the drag of a satellite in low Earth orbit. And again, the monotone version of this deep Gaussian process is better than a regular Gaussian process, better than a treed one, and also better than an ordinary Gaussian process. So that's my talk. I'm a big believer in reproducibility. All of the code for everything that I've shown you is available on this Git repository. I don't use GitHub. It's because back in the day I had to make a choice between GitHub and Bitbucket, and I made the wrong choice. And I stuck with it, as anyone should. But this is just a Git repository. You could download all the code for what we talk about in this paper. I think there's a lot of potential for building priors that have features of interest. I just did monotone, but you can imagine you might want unimodal, functions that just go up and come back down. Or maybe you want an asymptote, functions that go up monotonically, but then don't cross a certain threshold. There are lots of physical examples where you know stylized facts like that about your process, and you don't want to write them down in terms of systems of differential equations or something like that because you don't know them, or because maybe you believe those systems would be too constraining or put too much information in. I think there's a lot of potential for doing transformations like the ones I showed you in order to respect those facts about the system. This is work of Annie Sauer here, but now she's Annie Booth, who was a PhD student at the time, but is now a colleague, and Stephen Barnett, who just finished his PhD and has gone to Los Alamos to work with colleagues over there. Thank you very much for listening. It's a thrill to be here. Can I just point at people? All right. Good question. You could sample your input points, and then that would save you some linear interpolation in order to make predictions, unless you wanted to specify your predictive grid at the same time. So the reference grid is allowing you to not specify your prediction locations at the same time. If you're willing to do that, then you can make that your reference grid. And the only downside would be that now you've got to do matrix inverses on the order of whatever number that is cubed. So it'd be computationally more challenging, but it would work. And it could potentially have some advantages. But this data set here involved in the satellite drag is tens of thousands. And you can't do you can do one or two matrix inverses of that size, but you can't do thousands.
But can you, how,
Yeah, you're right. So there's this method. David Dunson has a paper too, but didn't have code for us to try. I would say the biggest difference between our idea and those papers is that we are generating functions that are monotonic. It's a generative monotonic process. Instead of these other methods are more optimization based. They've got some constraints built into an optimizer and they're trying to maximize something. And so the flavor of inference is different, but also at any particular part of the process, like when you're maximizing, you may not actually have a monotonic function. It's only in the limit in solving the mathematical program that you get an answer that's monotonic. This one is more optimization. David Dunson's is more sampling, but we didn't have any code to try. Thanks.
I think he has some space in the schedule now, so.